Today we will learn about the power series solution of ordinary differential equations. This method is very much important in solving differential equations encountered in electromagnetic theory, in quantum mechanics, etc. Before starting, it is worthy to mention that without knowing the basic concept, it is difficult to understand the solution of very important ODEs. In the first part of this lecture, we will try to learn about the basics of series solution that will include power series representation of elementary functions, some important theorem which will help us to understand this method in true sense, and in the next lecture we will try to solve some important differential equations. All the elementary series are often derived either as a Taylor series or Maclaurin series. Taylor series with center at x is equal to a of the function f is a power series. Let us expand a function f of x in terms of Taylor series. F of x is equal to f to the power n evaluated at x is equal to a divided by n factorial into x minus a to the power n, and the summation runs from n is equal to 0 to infinity. Now this power n actually represent the inner derivative of the function evaluated at point a. Now we can expand this function term wise. The first term for n is equal to 0, that will be f of a, the function itself evaluated at point a, where we know that 0 factorial is equal to 1 and x minus a to the power 0 is also equal to 1. So the first term is f of a. The second term will be again f of 1. So this will represent first derivative evaluated at point a divided by 1 factorial x minus a to the power 1. The next term for n is equal to 2, that will give us the second derivative of the function evaluated at point a divided by 2 factorial x minus a whole square, and the series will continue. So one can write in term wise expansion the Taylor series f of a plus 1 factorial is equal to 1. So f prime a into x minus a plus 1 by 2 factorial f double prime a x minus a whole squared and higher order term. Now similarly we can expand Maclaurin series which is centered at x is equal to 0. So the same function can be expanded in Maclaurin series like f of n. Now the function is evaluated at x is equal to 0 divided by n factorial x to the power n and the summation again runs from n is equal to 0 to infinity. Now again we can expand this term. For n is equal to 0, we will get the function itself at x is equal to 0 plus first derivative of the function at x is equal to 0, and 1 factorial will be 1, that is into x. The next term will be n is equal to 2, that will represent the second derivative, evaluated at x is equal to 0 divided by 2 factorial into x squared, and so on. So these are the two series which are the basics of the expansion of any function. Let us find the series solution of cosine of x. So the function f of x is cos of x. Now we will find the derivative of this function. F prime x is minus sine x. We can further differentiate it. The second derivative of this cos function will be minus cos of x. The third derivative of the function minus cos of x will be plus sine of x. Similarly, the fourth derivative of the function will be cos of x. Now we will evaluate these functions at x is equal to 0 to imply the Maclaurin series. So f of x at x is equal to 0 will be equal to cos of x at x is equal to 0, and you know cos 0 is equal to 1. Similarly, we can find the derivative at x is equal to 0. So f prime 0 will be 0 because sine 0 vanishes. F double prime 0 will be equal to minus 1. F triple prime 0 will be equal to 0. And the fourth derivative of the function at x is equal to 0 will be 1. Now we can plug in these values in Maclaurin series to find the series solution of cos of x. So Maclaurin series can be written as in term-wise expansion f of x, f of 0 plus f of prime 0 into x plus 1 by 2 factorial f of double prime 0 into x squared plus f triple prime 0 by 3 factorial x cube and the higher order terms. Now the given function is cos of x, f of 0 is 1, f prime 0 is 0, and now f double prime, that is minus 1. So that will be minus 1 by 2 factorial x squared. Again, if triple prime vanishes, so this will be 0. And the next term, that is 1 by 4 factorial f4 prime, that will be equal to 1. So that will 1 into x power 4, and series will continue. So cos of x can be written as 1 minus 1 by 2 factorial x squared plus 1 by 4 factorial x4 and so on. So this is the series solution of cosine of x. Now we can find the series solution of the function 1 over 1 minus x. Uh, the function given that is 1 over 1 minus x, so we can find the first derivative of the function, that will be equal to 1 over 1 minus x square. The second derivative of the function, that will be equal to 2 divided by 1 minus x cube, and so on. So now we can plug in the values in Maclaurin series here, and we will find that f of x, which is 1 over 1 minus x, that will be equal to f of 0, that will be equal to 1, f prime 0, that will be equal to again 1, so that will be 1 into x, f double prime, that is 1 by 2 factorial, so f double prime will be 2 into x squared, and so on. So one can write this function 1 over 1 minus x as a 1 plus x plus x square, and so on. And this can be written in compact form as summation over n started from 0 to infinity x to the power n. We can also write the other elementary function in power series expansion. The compact notation of cos of x will be equal to summation n 0 to infinity minus 1 to the power n x power 2n divided by 2n factorial. Similarly, sine of x can be expressed as n 0 to infinity minus 1 power n, and here the x power 2n plus 1 or 2n plus 1 factorial. So this series will be an odd series. Exponential series can be written in compact form as x to the power n divided by n factorial. Similarly, you can write all the other elementary function, cos hyperbolic x, sine hyperbolic x, and many more. Power series operation. Sometimes it is rather awkward to compute the Taylor series because the way in which the successive derivative grows in complexities. Try it for tangent x. Fortunately, power series may be manipulated algebraically in much the same way as polynomial. For example, if we have two functions, that is f of x is equal to summation over n a n x to the power n, and another function g of x that is equal to summation over n bn x to the power n. Now we can add these two series algebraically, like f of x plus g of x and that will be equal to summation over n an plus bn to x to the power n. This kind of algebraic manipulation of the two series is called term-wise addition. Similarly, we can multiply the two functions f of x into g of x, and that will be equal to a naught plus a1x plus a2x squared into b naught plus b1x plus b2x squared, and so on. Now we can see that the first term will be constant a naught b naught. The second term is a naught b1x, and similarly a1 b naught x. So we can common out x. A naught b1 plus a1 b naught into x. The third term can be written as, which is the coefficient of x squared, that will be a naught b2 plus a1 b1 plus a2 b naught x squared, and so on. Now this can be written as summation over n cn x to the power n, where cn can be written as cn that will be equal to a naught bn plus a1 b power n minus 1 plus a n b naught. You can now check it for n is equal to 0 and you will get a naught b naught. For n is equal to 1 you will get a naught b1 a1 b naught. Let's do an example of division of the two series. For example, we have sine of x divided by cos of x. So if sine x series and cos x series are divided, we will get tangent x. Let us do it. Algebraically, we are dividing two series. Sine x series, that is x minus x cubed by 3 factorial, which is 6, plus x5 by 5 factorial, which is 120, and so on. So now we are dividing this sine series by cosine series, and cos of x 1 minus x square by 2 factorial plus x square by x4 by 4 factorial, that is 4 factorial is 24. Now first we will multiply this series by x to cancel out the first term in the sine series. So we will do it x. Now if this series is multiplied by x, we will get x minus x cubed by 2 plus x5 by 24, so on. We will change the sign, minus, plus, minus. So the first term will cancel out, this term, and we will left with this term, which will be equal to, if these are added together, we will get x cubed by 3 minus, similarly we can add these two terms, so x5 by 30 and so on. Now to cancel out this coefficient, this coefficient, we should multiply this series by x cubed over 3. So now we are multiplying the series by x cubed over 3, and we will get x cubed over 3 for the first term, and then we will get minus x5 by 6 and so on. So now we will add it after changing the signs, and again we will see that this first term will be cancelled out, and we will left with to the x power 5 divided by 15 and so on. So the next term here in the series, because this is 2x5 by 15, so the next term in this series will be now 2x5 by 15 and so on. We can continue. Now look at this. This is the series expansion of tangent x. So tangent x series can be written as x plus x cubed by 3 plus 2x5 by 15. So the functions which can be expressed in infinite series can be manipulated algebraically to avoid any complexities. Now we will discuss some important theorems about the series solution method. Theorem 1. Term-wise differentiation of the series. Let us consider a function f of x that is equal to summation over n, and n started from 0, and this is an infinite series, an x to the power n. We can write this series in term-wise expansion a naught plus a1 into x plus a2 x squared plus a3x cubed. And now if we differentiate the above function with respect to x, we will get, because a naught is constant, so this will vanishes. We will get a1 for a1 into x, and we will get 2a2x for the third term. For the fourth term in the series, we will get 3a3x squared. So we can write a1 plus 2a2x plus 3a3x squared, and so we can see here that the power of x is reduced by 1 after first differentiation. Now we can write this term-wise expansion in compact notation as, now the series will start from n is equal to 1. So we can write n is equal to 1 to infinity, and the coefficient are 1, 2, 3. So we will multiply it here by n, and the x power is reduced by 1. So we will write it x minus 1. So this is term-wise differentiation of series. Let us do an example. We have a function 1 over 1 minus x, which can be written as in series form in 0 to infinity x power n, and can be expanded as 1 plus x square plus x cube and so on. Now if we differentiate this function, we will get on the left hand side 1 over 1 minus x squared, that will be equal to, because 1 is constant, so we will get 0. From the first term x we will get 1, and this term 2x, and the fourth term will give us 3x square after differentiation. Now the right hand side can be written as 1 plus 2x 3x square and so on. In summation notation, this can be written as n into x power n minus 1, but this time the series will start it from 1. So what we can conclude? We conclude that whenever we differentiate a function, the power of the x reduce and that of n will increase, and now it will start it from 1. If we differentiate it twice, then this index will start from 2 and so on. So important conclusion of theorem 1, shift of index of summation. Let us consider a series that can be written as n into a n x to the power n minus 1, and the summation is started from n is equal to 1 and goes to infinity. Now by shifting the index of summation by plus 1 in the series on the left, that is, we simultaneously increase the summation by 1, replacing n by n plus 1, and decrease the starting point, this starting point, by 1 from n is equal to 1 to n is equal to 0, thereby obtaining the series of right hand side as. So we will shift the series by 1, so the index n will become n plus 1 over here, this n. An now will become an plus 1, and here we also replace n by n plus 1. And now this index will be decreased by 1, so the summation will now start it from n is equal to 0 and goes to infinity. You can check now, both the series are same. That is, n is equal to 0 to infinity n plus 1 a n plus 1 x power n. So this reflects that shifting of the index of the summation is possible. This procedure is valid because each infinite series is simply a compact notation of single series. More generally, we can shift the index of summation by k. The process of determining the coefficient in a given series like y is equal to summation over n goes to infinity a n x power n, so that it will satisfy the differential equation depends upon theorem number 2, uniqueness of power series. If we have two series, that is a n x to the power n, that is equal to another series which has coefficient b n x to the power n, for every point of x in some interval I, then remember a n should be equal to bn for all n values that are greater than or equal to 0. In particular, if a series a n x n is equal to 0, it follows from theorem 2 that a n's z will be equal to 0 for all n greater than or equal to 0 for all power of x. Conclusion of Theorem 2. Let us consider a series in which we are starting from the lowest power of x, that is x power k minus 2. The next lowest power is k minus 1 and it increases to k, x power k. The requirement that the coefficient of lowest power of x vanishes leads to incidental equation. It is very important to our analysis, which shows that from where our series solution must be started. In other words, it will give us the roots of the differential equation, and that can be shown by a naught. So this must be vanishes. Now, according to theorem number 2, the coefficient of x power k minus 1 must be vanishes independently, that is a1. And this will tells us the second coefficient is treated by setting a1 is equal to 0. The vanishing coefficient of x power k is ensured by imposing the recursion relation, and so on. So this will develop a recursion relation for us. So these three are the most important conclusion of theorem 2. Theorem 3, radius of conversion. A series solution must be checked for convergence and divergence. So given that power series a n x to the power n Suppose that the limit, r is equal to limit n tends to infinity a n plus 1 divided by a n mod. If a n plus 1 divided by a n mod is less than or equal to r is less than 1 for all sufficiently large n and r is independent of n, then an is convergent. And if an plus 1 divided by an is greater than or equal to 1 for all sufficiently large n, then summation over n an is divergent. So D-numbered ratio test is one of the easiest to apply and is widely used. So let us apply the ratio test to check for a series to be convergent or divergent. Test. Summation over n divided by 2 to the power n. So let an is equal to n divided by 2n and an plus 1. Now we are increasing the index by 1 on both sides, so an plus 1 will become an plus 1 divided by 2 to the power n plus 1. Now the ratio of an plus 1 divided by an that will be equal to n plus 1 divided by 2n plus 1 and whole divided by n to the 2 power n. This can be simply written as so this 2 to the power n will cancel out and we will left with n plus 1 divided by 2n, or that is 1 by 2 plus 1 by 2n. Now implying the limit when n is very much large, that is 1 by 2 plus 1 by 2n. When n goes to infinity, after putting n tends to infinity, we will get 1 by 2 and this is less than 1, so the series is convergent. We can take the radius of convergence is rho is equal to 1 over r, so that will become 2. Now this is our r. So that is 2. So the series will be convergent between -2, x lies between -2 and +2. Let us consider that f of x is given by c naught summation n goes from 0 to infinity n plus 1 divided by 3 power n x to the power n. Here the coefficient of xn is an c naught, and I am ignoring the summation sign. Already we know that there is a summation over n, so I am writing it c naught n plus 1 divided by 3 to the power n, and a n plus 1 will be equal to c naught. The numerator become n plus 2 and the denominator will become n 3 to the power n plus 1. Now we can take the ratio of n plus 1 divided by n, that is the ratio, and this will be c naught will be cancelled out, so we can write this as 3 to the power n into 3, and we will invert the an, so that will be 3 to the power n into n plus 1. So we will get now n plus 2 divided by 3 n plus 1. So now further we can simplify it, that is 3n plus 3. Now taking the limit for n to be very large, and that will be equal to limit n tends to infinity and we can divide this number by n, so we can, if we divide the numerator and denominator by n, so we will get 1 plus 2 by n, and in the denominator we will get 3 plus 3 divided by n. Now plug in n and we will get 1 over 3. Now the radii of the curvature, that is 1 over r, and that will become 3. So this series is convergent if x lies between -3 and 3. So the series is convergent. You can now check for n minus 1 factorial. So remember, these lectures are very much important for the understanding of the differential equation like Legendre equation, Bessel's equation, Liquori polynomial, which we will use in quantum mechanics too frequently.